he will present data-centric IoT platform for enhancing traffic flow management, Llama 4 model, SOC engineering case study. So the second presenter is Ryu Nishimura from NICT. And his title is IoT sensor network for infrasound monitoring. And the third presenter is Mr. Nasim Ahmed, Bangladesh University of Engineering and Technology. The title is the development of blockchain in smart grid using IoT. So this is the first session, and then session 2 is starting from 3:30 p.m. And in these sessions, there are one presentations with two speakers. One is Dr. Harin, and the other one is Mr. Yoshimasa Gunji. And the title is Case Report of Creating of Sensor-Based Smart Village with Disaster Resilient Distributed Area Communication Network applying NavNet technology in rural area in Sri Lanka. Okay, so let's start from the first speakers, and I will share. Okay. Just a moment, please. Okay, so let's start.
Mr. Chairman, Dr. Owada. Yes, today is a great opportunity for us to gather here again after the COVID-19 pandemic has already let us some free time so that we could come here in Sri Lanka and to enjoy the cultures over here, as well as to get together old friends and meet new friends. My name is Chowdit Aslogun. I'm from Chulalongkorn University, and in my team, we're working on the WISE network, future internet, and as an engineer, I'm the electrical engineering, communication engineering, but I'm also working on the transportation engineering. And the topic I like to share with friends over here today is the work that consumes my life, my team's life for the past 3 years. We've been focusing on trying to address the Rama 4, which is the name of the road, to Chulalongkorn University in Bangkok. And as probably if you have visited Bangkok, Thailand, once at least you know that the traffic is pretty jammed. So we're trying to see how we could use some of the new opportunities, technologies that we've learned in our communities over here in order to try to address some of those problems. Here's a topic that I need to share with you. Data-centric IT platform for enhancing traffic flow. Traffic obviously is not communication traffic. It's a road, cars traffic, and we need to manage those flows. We approach it with the end users in mind, which means that we're trying to address not only from the viewpoint of the engineers, but from the social aspect as well. Been taken for granted in designing the approach used in our project over here from mainly 2 projects that we have for the issue Connect. One is the IoT Cloud Server 10, and the other is the Open Federation 10 Triple Plus. And over here, we think of those know-how as like enablers of the technologies that allow us to connect the dots We connect the dots for the other two projects that as a prerequisite already started some study in network in Thailand. One is Saturn model project. Saturn is the name of another word whereby to that word so-called ramful. There is the acknowledgement to all of our collaborators for if we are going to address the test bed that's not only inside the laboratory vicinity, but it's a test bed that's for the whole world network. And so we need permissions and authoritative state enterprises, the police, the city governance office, us at the University. So we signed a random action to work on this whole study together. We have received support from Toyota Mobility Foundation, Japan. This is Bangkok. The area of Bangkok is like 50, 30 kilometers east west, north south. However, Bangkok also received a lot of traffic. It's not only from residents inside that small area, rather it has a continuously spanned resident areas all around the metropolitan area. And that would be like 16 plus million people move in and out, having mobility demands across this small area today. This is my area considered in the project. We've already heard two names. One is Brahma 4, the other is Saturn. Those are two interconnecting roads. The map from the left-hand side to the right-hand side, that's about 15 kilometers. So you could have the dimension in mind. Chulalongkorn University, my university, is in that region. So in this area has potential the sink and the source of the traffic demand. A lot of traffic that try to cross this river, it's called the Chao Phraya River, from the western side and coming towards the east. Around my university, it's a business district, a central area of Bangkok, so it's a work area during the day. And the evening time, then in this direction, the traffic happens. Since there are only like a couple of not so many budgets across the river, so dams develop unavoidably and propagate upstreams to all the other areas. This is how it looks like it's when dam develops. This is on Saturn Road. So it's the road, it's not the parking lot. The right-hand side also we have a lot of motorcycles. Just like waiting for the green light. A lot of high-rise buildings. Part of the roads can be serviced by public transportations, or there are more and more public transportations ongoing, but not enough yet. Challenges due to three problems that be oversaturation compared to the supply. When there are bottlenecks, and if not managed properly, they develop into gridlocks. So it's a locked as a loop inside the topological network structure. This is the goal of our project, Grammar Film Project. Looking at ways to mitigate the condition on the network, using the social engineering projects And trying to combine traffic engineering principles, the IoT technology, the cloud technology, all kind of things that we already taken for granted in our community over here in Japan. Try to see how we could plan experimental trials on site, do it for real, not only on paper. See the insights that can be gained. Some of those will be shared with the Japan community today. And we like to develop management roadmap guideline and as a recommendation to all the state authorities that are responsible for managing all the traffic flows. And since we are in the academic side during the university, so we look at how we could formulate the collaboration of public-private academic partnerships in learning, tackling this problem by the new technologies together. This is a feature that's going to be like assumed time and time again throughout the remainder of this presentation. The three parts inside is a cloud at the center, and that is a data integration computing cloud runs using the Kubernetes. And that supports on the left-hand side all the IoT sensors that we managed to install in our projects, as well as to ask for contributions if those sensors are already available by other organizations. The right-hand side is all the applications that we deploy to run on real-time traffic flow management. Let's focus on the source of the data. This is great because big opportunities, at least from our team's point of view. For now, we have received like GPS data from a collaboration these companies. We also have data that are available in the state, the public facilities, like Bank of Metropolitan Administration or the BMA. We've already got some CCTV, cross-circuit TV streams, as well as the traffic signal light control data. The ITEC, Intelligent Transportation System, that's a foundation. In Thailand, the non-profit foundation, they also aim to provide some of the data, the incidence data, real time to our project. Some of the sensors we have to develop and install, make it work in our projects well. Signal control sensors at all the junctions, scanning traffic sensors. Let's go through each of the sensors. I'm just going to show you like some pictures so we could go quickly through the availability of the sensors. These are CCTV locations. Scheme around there. So here. From this to that, it's about like 5-6 kilometers. This is part of the network. I just capture it so that you see, okay, these are the CCTV that we link into our system. This is how they look like. Not the bird eye view, so visual analytics will be a little bit difficult, but it's good for the traffic police to see and to analyze in close details in strategic locations. This is at the corner of Chulalongkorn University. We installed the new camera in bird eye view, so that we'll be able to run some video signal processing, machine learning, in this case, to detect the stopping car incidents on the bridge. And this is kind of the blinded spot that the police will be able to see. So once we have this in place, then AI that okay, right now there's an accident happening on the bridge, and police will be able to act promptly without any delay. Apart from that incidence detection, we also running the signal processing again, but here for counting for the traffic volumes, the amount of the traffic, as well as to classify vehicle types like it's cars or tuk-tuks or the buses or something like that. And we wanted to check that, well, those signal processing guys, they're working accurately enough for our purpose. This is another one, the signal control data. Over here, we're getting from main junctions, and we're trying to see the map shows on the x-axis from midnight to another midnight the same day. Y-axis, that is the phase number. Phase, it means like right or way, which directions get the light. So we'll be able to see the pattern of controls, which is also important for improving the control strategies itself. And this is how it looks in the signal control box. Wires, and that is our device, which we have hooked this 4G cellular network, send all the data into the infrastructure time series database so that we'll be able to get that every 1 second. The IPAN sensor, Bluetooth sensor, so sniffs the MAC address of the Bluetooth, which could be like audio system inside the car. And so we have timestamp. And once we know the timestamp of that MAC address, that same address comes to another timestamp at another location in space. So we calculate the travel time, the speed. This is how we install the sensors. Basically, we install at most of the junctions because we would like to know the details for each hop, each link, what is going to be the travel time. In the end of the talk, I focus on blue and dark blue selected areas, but not the remainder of the areas. Not enough time. Let's start with this one, the dark blue. This is the central area of all our test network over here. It's an important area because it's interesting. Practically and academically, there are two gridlocks that may happen. They coupling together. Small gridlock happens first. Once it's locked, a part of the road in the small gridlock will also trigger another larger gridlock to happen subsequently. So they're coupling. And that is also a good chance if we could prevent the small gridlock from happening, then the large gridlock would automatically be subsided. This is from the GPS data of the taxis, and we run the analytics for rush hour traffic. See the small gridlock, and then we run control-wise, counterclockwise from one location, and then we linearize it, put it in the scale, and we analyze on the speed as display as how much intense that weight means. Well, if it's too much weight, then the car stops. If it's quite light shade of the weight, it means free flow. So we focus, therefore, the x-axis from midnight to another midnight again. Y-axis, it is the location contour clockwise direction. And we would like to see when you have like more or less all red vertically, it means the yes, completing the loop of the log. Now, when the scrolls are open versus when the scrolls are closed on the left and right hand side. So we're able to know not only qualitatively that block happens, but when exactly it happens. What is the initial cause of that? To see by our own eyes as well, not only to trust on the data. So we just survey all the area in order to confirm the small. Yes, they really happen. Let's move to the right-hand side. How can we do anything about that? Well, information in real time to traffic police authority responsibility to manage and to control all the flows. Rush hour morning, rush in the evening. So this is the central command center which we have installed our displays in there for the police to see. But it's not enough because one man only seeing the whole big picture, but one man has only two hands, lines, restricted control, restricted space. So all our traffic volume distributed throughout the whole network installed 12 locations to control 13 junctions, responsible by 7 police districts in all the dots. This is how it looks like inside those distributed rooms. They're small ballrooms, not the big ones. So you see our space, you see traffic police that you are trained in order to understand and make use of the information. This is at the display. So what we show to the traffic police? Show what time CCTV streams for only some important traffic directions and show the incidents list. Like accident happened, when, where, show the signal control of not only responsible junctions, but all the neighborhood junctions, so that they will be able to with some coordination strategies that we could work together. Show the map as well as some of the outputs from travel time sensors. It's not enough still. If you want to deliver the technology to the end users, you have to reach them. This is my team, and we brainstorm with the traffic police. We call that knowledge management session. In fact, the expertise is in doing all the stuff very much belong to their domains, the traffic police domain. We give them the real-time information. After all these management sessions, which last for about 2 years, we standardized the procedure. We print the manual. And this is going to be the manual which shows on the left-hand side the bus picture. In the morning, what flows direction you have to prioritize. In the evening, what are the flows you have to do? And you have to do it is the whole team seeing the big elephant as one elephant together. So I compare elephant to traffic flow, big traffic flow. The what triggering events you should focus on to change from phase number 1 to phase number 2, phase number 2 to phase number 5. And what is the formula for circulating those phase sequences? So this would just be like a list of events that we have to take a look. Once we have put volume in place, is it improved? So this is based on 4 months of the social experimental trial results from November last year to February early this year. Before installation of traffic volume, during the installation in the January, and after everything is already completed. And then we compare the duration of the phases of the traffic signal, which are abnormal phases. Abnormal phases are the so-called phases that the police are forced to use. Some incidents happens, like queues spilling back from the downstream, so they're not allowed to go in all the possible non-conflicting directions. So you have to use like some partially allowable phases instead. So we just record that from our IoT sensor data, and then we'll be able to see that if we compare before installation versus during the installation, well, not much improved, basically. But after everything completed, then 11% improved. So it means that the traffic police are much less likely forced to open some abnormal phases during the rush hours. We also try to run some computer simulation, like digital twin stuff. This is the offline one. This is a simulation that we run microscopic in that same area, but now we repeat the whole thing inside the cloud. But we'll be able to study and to repeat that with much more convenience in much faster way. That study with accurate traffic data given in the volume versus without accurate traffic data given in the volume, then what would be the jam lanes that happen on the road? What would be the mean variable speed of the cars that could be seen? And we compare in both the small gridlock loop, one, and the large gridlock loop. One. Our computer simulation will predict that the power of real-time and accurate traffic information given to those responsible for management of the traffic flows will benefit you for 30% improvement, up to 67% improvement. On the AI that we have implemented in order to stimulate the decisions of the traffic police based on the agent deterministic policy gradient, which is just one of the agent neural net thing that we have developed. The last area I want to show over here, rightmost area. The rightmost area, there is a small bottleneck that could be developed into a gridlock as well, as we have seen in this map. Block would happen in a very strange way because there will be traffic coming along this area, which I am moving here, turn right over here, take a U-turn, and then coming back like that. What kind of vehicles would flow from here, taking that right turn, U-turn, turn left, and coming to the same location that it used to be? Is the minibus taxis, it's public transportation. So we analyzed that and then we tried to see what is the root cause of that bottleneck. And we have found that it's people crossing the street, crossing back and forth. Let's show the video, shall we? on the left-hand side. Just before anything about it. So you could observe that one people, another two people. So they just keep walking across the street. Even randomly on demand, right? This problem actually is very simple. On the right hand side, and let me now zoom in a bit. Just need to tidy those behaviors by having like 12 fragments and just going to more people crossing all together and the traffic police in the middle try to make things very smooth. So the solution actually is very straightforward and very simple, and that's good because they would like to find that kind of simple measure that can be implemented very easily, that will be overlooked. Its benefits. So we just install a lot of sensors all around, put it in place, and that's the result. Part of the box, the pedestrians crossing the street in bigger group signs, and as a result, from the 3 hours during the evening rush hour, the total crossing time is reduced by 23%. Understandable. Because from that, the flows has increased by 10%. At the higher speed of 8%. So now we have quantitative evidence, not only qualitative one, in order to prove that simple measure like that actually works. And it doesn't cost anything at all. So having the data, I think that is a good decision making point. In conclusion, from our experiences in this project, 3 years that our team's been working on, is a good technological opportunities. We have proved that it's possible, feasible for the large scale, cost-effective deployment. We have investigated one system architecture that works with the automation, combined traffic engineering, IoT, cloud, big data analytics together. And we provide the quantitative search experimental results in order to confirm that by having data enhancement, effectiveness for real-time traffic flow management is possible. Thank you very much.
Do you have any comments and questions for these presentations? Oh, okay.
Thank you for a fascinating presentation. It would seem that the system is always on the verge of a chaotic state. You adjust the traffic light signal timing dynamically based on the flow rates that you're picking up. Are you also, so in Singapore, they use a social engineering technique for the mass rapid transport system, where they'll randomly divide people to send them to the most appropriate station to avoid congestion at a particular time. Are you using any sort of application for feedback to the drivers to push them to a particular flow pattern that you wish to that could enhance the gridlock stability.
Right. I think there is a ongoing work that's around that advanced traveler information system. Yes, by giving important information, for example, real-time availability of the parking lots.
Okay.
So that cars do not need to randomly shop around to go to where they want to park. You could go there, park as quick as possible, and go doing whatever that they want in that area. And as for the real-time detour, when congestion occurs, I think that the private sectors, like navigator companies, they have already done that.
So are you feeding into things like Apple Maps, Google Maps, Waze dynamically, or are they still separate and maybe pulling out of your systems in a different way?
At this moment, not yet, because data has borders, ownerships. And so the data that we have collected, we would like to make it open. But if the private companies would like to get something out of it, then maybe we have to negotiate something so that they give something back, giving in terms of data exchange or something like that.
So it's always good to fund your continuing research as well by doing that.
Right.
So what are the inflection points for those phase changes? You mentioned that there were kind of various phases throughout the day, and the police will adjust for a particular phase. How much notice do you have in terms of how much forenotice do you have in terms of that phase change requirement?
That's quite complicated, and it depends from one junction to another junction. Yes, but from the knowledge management manuals, mostly they will look at upstream queue length, building up downstream queue length to see if they can let it go, real-time upstream occupancy to see if the remaining queue is still a lot that they have to try to throw it out, something like that. But wider area incidences are also important, like gridlock about to happening or not, something like that.
I think you've already answered how do you perform social engineering for the drivers? I think you've already answered that. Thank you very much.
Thank you very much for your questions.
Thank you. Is there any questions and comments?
Okay.
Thank you for a nice presentation. One thing I would like, you talked about the Bluetooth, use of the Bluetooth of a car for the signal for the processing. What happens and what are the statistics that people will be using the Bluetooth, keeping their on while driving? And second, any other sensors that you have placed on the roads other than the car and other things that I would like to know about that?
Right. There's a lot of sensors. Bluetooth is one of them. We have collected the amount of the detectable MAC addresses, but we have not analyzed on the penetration rate of cars to contribute to the Bluetooth sensing data just yet, because it is wireless and it's a little bit challenging to.
It would maybe require some permission to, if we are accessing my Bluetooth device MAC address. Obviously, that may require permissions, and then maybe.
Right. There's a Privacy Data Protection Act.
That's
we have to abide by.
Abide by, yes. Thank you.
Right.
Just a last question. I don't think you did mention there was a permission model required for actually gathering that Bluetooth data. You're just doing it. How long do you actually keep that data after you've processed it? Is it stored forever, or what sort of, when do you delete it?
First of all, at this moment it's trial. So we would like to keep it as long as possible without deleting it. But with the condition on like using for educational and not releasing it out to the public just yet, right? So so over that condition, it is pretty okay. But if we would need to release that, maybe secondary data after we have already analyzed it, something like that, but not the raw data.
Are you looking at using that data for any other crime management? So I could presume that, you know, a crime could be reported, that Bluetooth address could be identified within an area. The police could be using that to track a suspect in real time.
Not yet.
Okay. And has anyone actually hacked your system by using Bluetooth techniques to adjust things?
Luckily, as far as I know, not yet. So, yes.
So you've just raised a challenge for us for our next APAN meeting in Bangkok.
Right. And yes, if you have some suggestion, like in order to like hardening the system a little bit, yeah, okay. I would love to learn.
Cool.
Thank you.
Okay.
Okay.
So the time is a little bit pushing, so let's move to the next speakers. Thank you very much.
Very much.
Okay. So the next speaker is Ryo Nishimura. So he's virtually represented. So if you are ready to present, please start.
Can you see my slide?
Yes.
Okay. Oh,
Please start.
okay. Hello, I am Ryo Nishimura from National Institute of Information and Communication Technology. It is a great honor to introduce my research topic about infrasound to you at APAN 56. First of all, I would like to express my gratitude to session chair for giving me this opportunity. I also apologize for this remote presentation from a hotel room. I am now on a business trip in Japan. My sound quality may be bad due to reverberation or something another reason. I hope that it would be acceptable to you. Today, I will talk about IoT sensor network for infrasound monitoring. This is outline of my talk. As an introduction, I will begin with the fundamental of infrasound to those who are not familiar with it. Then we will see devices for infrasound measurement, which include not only conventional ones, but also a newly developed miniature microphone. After that, I would like to show an ongoing attempt to build an infrasound sensor network. I will also demonstrate an application example of it. That is direction of arrival estimation using infrasound signals captured by the sensor network. Finally, I will give some concluding remarks. What is infrasound? Sound is called differently as its frequency changes. Humans can hear sound within a frequency range from 20 Hz to 20 kHz. Sound in this frequency range is called audible sound. If sound frequency is higher than this region, it is called ultrasound. Ultrasound has been already used in several applications, such as sensing inside the human body or detecting an object around a car. On the other hand, sound of a frequency lower than the human audible range is called infrasound. Such sound has wavelengths of a range from a few dozen meters to hundreds of kilometers. Therefore, it is not easy to generate infrasound artificially. A strong natural phenomenon such as volcanic explosive eruptions, thunders, and tsunamis can sometimes generate infrasound. They all may result in a natural disaster. Therefore, it is considered that monitoring infrasound would be useful for early detection of natural disasters. Japanese people have experienced an example of its potential just 12 years ago when Great East Japan earthquake happened. The waveform shown on this slide indicates the atmospheric pressure observed at Mizusawa Observatory. Earthquake occurred at 5:45 in Coordinate Universal Time. Soon after that, high-frequency pressure fluctuation was observed. This is considered a result of surface vibration of the ground due to seismic waves. Approximately 30 minutes later, tsunami arrived at Ofunato, which is a port town here. During this time period, there was a large fluctuation in pressure, as indicated by the red circle on the slide. This is considered infrasound generated by the swell of the sea surface at the origin of the tsunami. It is noteworthy that the infrasound arrives approximately 15 minutes earlier than the arrival of tsunami. Therefore, if the relationship between infrasound and tsunami has been well investigated, we might be able to predict the arrival time and the scale of tsunami more accurately. To capture infrasound signals, we need to use suitable measurement devices. We can use microphones to capture audible sound. What about infrasound? For this low-frequency region, we can use microphones especially designed for infrasound. As the frequency goes lower, microphones lose their sensitivity and we need to use pressure sensors. There are two problems here. The first problem is that there is a gap in available frequency range between pressure sensors and infrasound microphones. The second problem is that, in general, the wider the available frequency range becomes, the more expensive the sensor is. It may pose an obstacle in constructing an IoT sensor network because the number of sensors is an important factor for IoT sensor network. As described in the previous slide, there are not so many sensor devices available for infrasound measurement. Most of them have been developed for scientific research. Different from microphones, pressure sensors directly measure atmospheric pressure itself. Infrasound is considered as its AC components. Therefore, it is important to discriminate infrasound from the pressure variation caused by the weather. We can do it by estimating its traveling speed, because infrasound travels at the speed of sound. To do that, we need to deploy multiple sensors spatially distributed. In this respect, MEMS pressure sensors can be a promising solution because it is small and inexpensive. However, it is usually realized at the sacrifice of its achievable precision. This table shows the specifications of the sensor devices presented in the previous slide. The first three columns are those for the microphones, and the last two columns are for pressure sensors. In general, microphones have higher precision, but a narrower measurable range in both pressure amplitude and frequency band. MEMS sensors have larger self-noise level than other sensor devices. However, we think that it is acceptable for infrasound sensing because ambient noise is usually larger than this level, although it depends on frequency. This slide shows some examples of MEMS pressure sensors commercially available at present. Its accuracy is not good as microbarometers. Microbarometer is a general term to represent barometric pressure sensors having both high frequency and high precision. Infrasound is a signal of time variation in atmospheric pressure, and in this case, what is important is not accuracy but precision. In this respect, MEMS sensors can be acceptable for infrasound sensing because its precision is almost less than 1 Pascal. I would like to introduce a new microphone categorized here. It has been recently developed by a Japanese company called Rion, exploiting a technique originally used for manufacturing hearing aids. It has two models, depending on its sensitivity, so that it can cover the wide dynamic range of infrasound. This slide shows results of comparison test with BK type 4964, which is a 1/4 inch typical infrasound microphone. The upper panel is the original result, where we can see that there are 28 decibel difference between the high and low sensitivity models. To make it easy to compare, these three curves were normalized at 250 Hz, resulting in the lower panel. From this figure, we can tell that Rion XE1L has frequency characteristics comparable to BK type 4964 within a frequency range between approximately 0.2 Hz to 3 kHz. Hence, we consider that it can be a candidate for use in an IoT sensor network for infrasound monitoring. So far, we have seen sensor devices which are suitable for IoT. Now, let's think about constructing a sensor network. In fact, a global infrasound monitoring network already exists. It was constructed by the Comprehensive Nuclear Test Ban Treaty Organization. Therefore, its fundamental purpose is to detect and localize a nuclear test performed somewhere on the globe. This photograph on the right-hand side of this slide shows a typical infrasound monitoring station used there. It consists of 4 or more microbarometers, each of which is connected to multiple perforated pipes to mitigate wind noise. As can be seen, it occupies a large area on the ground, and its location should be far from interfering noise sources. Such a complicated requirement is not suitable for an IoT sensor network of domestic scale. Hence, we decided to use more compact sensing systems to build a sensor network. For example, this is an infrasound monitoring package developed by Japan Weather Association. The main sensor is still a microparameter. It is equipped with a data logger to store the captured data and communication device to send it. Researchers at Japan Weather Association deployed this equipment to some schools in Japan. It has not been well verified yet, but influence of noise can be mitigated to some extent by setting this equipment inside a building like a school. They also operate a website called Infrasound Monitoring Network, where anyone can see the locations of the deployed infrasound sensors and signals captured by them. Cooperating with Japan Weather Association, some other research institutes feed their captured data to this website to make it publicly open. One of them is National Institute of Information and Communication Technology, which deployed their monitoring systems in Kagoshima, Tokyo, and Miyagi prefectures in Japan. Infrasound data observed at 5 locations in Miyagi prefecture are available at the website. Other than National Institute of Information and Communication Technology, Kochi University of Technology and the University of Tokyo also feed their obtained data to this website. So please visit there if you have an interest. This is an example of the infrasound data captured by this monitoring network on 15th January 2022, when Tonga submarine volcano erupted. The upper panels show infrasound data observed by our sensor devices deployed in the 3 prefectures that were previously mentioned. The lower panels show the time delay of arrivals between all the pairs of observation points for each prefecture, calculated based on cross correlation. You can see that the time delay of arrival kept constant for a while after the first arrival of infrasound. It means that the infrasound coming from a single direction lasted for a couple of hours. In order to estimate the direction of arrival and sound speed simultaneously, we construct a system of equations for time delay of arrival, considering the geometry of sensors shown in this slide. In this slide, only one pair of sensors is considered, and therefore only one equation can be derived. We can consider all the pairs of available sensors to construct a system of equations. This is a possible formulation to estimate the direction of arrival and the sound speed. They are respectively represented by theta and c in this slide. Therefore, vector x is the unknown parameter to estimate. Other parameters are obtained from the sensor geometry and the observed infrasound signals. This formulation is considered as a minimization problem with a single constraint. As you know, there is a well-known approach to solve this type of optimization problem. That is the method of Lagrange multipliers. The problem here is the constraint is not a linear equation. If it were a linear equation, a closed-form solution would be obtained. However, it's a second-order equation in this case. Fortunately, 2 unknown parameters can be simultaneously cancelled, as shown in this slide. As a result, a closed-form solution can be obtained, as presented in this slide. This is an example of applying this algorithm to infrasound signals captured by the infrasound monitoring network. Estimation of the direction of arrival and sound speed were conducted for each prefecture individually. The right bottom figures display the estimation results, traveling speed and direction of arrival. When the estimates of direction of arrival are visualized as azimuth lines on the map, we can see that they are directing towards the location of the volcano, approximately 8,000 kilometers away from Japan. Finally, I would like to give some concluding remarks. In this talk, we overviewed infrasound monitoring. To the future, further research and development will be needed on the topics listed in this slide. Advanced technologies for IoT will expand available locations for installing infrasound sensors. Signal processing plays an important role to achieve reliable estimation regardless of environmental conditions. Of course, cooperation with many researchers in various areas would be necessary to make a new information source will be necessary to make infrasound further usable. I hope that infrasound will be available as a new information source for a practical disaster management in the near future. That's all. Thank you very much for your kind attention.
Thank you very much, Nishimura-san. Is there any questions, comments?
Thank you for a nice presentation. There's a one question, one observation, or one like I can say, just looking forward for the idea that actually the sound is usually detected by its pattern. It's a symmetric pattern. And obviously in the infrastructure, in the infrasound, if you are looking for a sound or you are looking for a pattern which is an irregular pattern. So how you can distinguish between the useful noise, I must say, or a non-useful noise? For example, if you mention about the tsunami infrasound, obviously, whenever the next time it comes for Godbit, so obviously it may have a different pattern. You don't have a regular pattern of it. So how you can distinguish? One may discard it as considering as a noise, and one might think that it's a voice and hunting for it and grabbing it. Okay, maybe it's a useful sound. So how you are making a distinguish between a noise and a useful noise? Thank you.
Thank you for your question. First of all, we didn't use spectrum at this moment. We use time delay of arrival. So it means it uses all frequency components simultaneously. Analysis was carried out in the time domain rather than frequency domain. So maybe, as you said, are you considering frequency analysis may give more helpful information, but at the moment we didn't use it. Does it answer to your question?
Let's rephrase my question. That you are looking for something that has never been seen before, that has never been heard before. So how you can distinguish that it's a useful information for you? If you're just in a black box, you have a lot of signals coming in the infrared, and you don't know which pattern you have to detect. Each of the pattern can be useful, and each of the pattern cannot be useful. That is my question. For example, you are more obviously interested in insight in that point. If I want to train my noise, obviously it's a symmetric pattern. So you first give it and then try to hunt for it pattern, and then you identify this is the Mr. XYZ speaking, or this is the particular noise. But in the infrared noise, you haven't heard it anything. So just I'm interesting to know that if you have some algorithm with you, if you have some logic that in your mind that this out of this infinite possibilities that you are looking for a one possibility, how? That's I'm
Oh,
interested to know.
well, we are estimating not only we use multiple sensors to estimate the direction of sound and sound speed simultaneously. So we can discriminate useful information and others by which location the sound coming from and how fast it is traveling. Infrasound travels at the speed of sound, but other signals, such as noise signals, has different sound speed, traveling speed. So we can distinguish them using such information.
The previous question is a lot of the surround sound recordings that you obtained or that others have obtained that could be fed to a more predictive model based on the spectral analysis.
Sorry, the sound quality is quite bad, and I couldn't catch what you were saying. Maybe other you use when you use other microphone, sound quality becomes different. Can you do that?
Of the sounds that you have captured that maybe we could use for future spectral analysis to determine the cause of the event.
Your question is if we use sound spectrum, it will help to determine the cause of the sound. Is it right?
Have captured. Perhaps someone more fluent in Japanese may be able to translate for me.
So your question is using some library?
Is your library, are you making the recordings available for others to do analysis on in the future?
So so sorry.
The data being collected will be available online for other users.
Yes. So このデータ自体は他の人たちに共有したりするんですかね。
先ほどお話したように、ウェブサイトで、はい、シェアはしてます。
Yeah. So this data, collected data is opened and shared to the other is on the website. So you can access the data freely. Yes. So the time is a little pushing. So let's go to the next speakers. So thank you very much for Nishimura-san.
Thank you.
So the last speaker is let's see.
Nothing.
The last speaker is also virtually. So Nasim Ahmad. So
Sir, I am online.
Yeah, you're online. Okay. So Nishimura-san, could you stop your screen sharing? Okay. So if you're ready, please share your slide and start presentations.
Thank you, sir. I'm Nasim Ahmed from Bangladesh University and Engineering Technology. I'm a master's student here, doing masters. So here's my presentation: development of blockchain in smart grid using IoT. First of all, convergence of blockchain, distributed energy, renewable. And IoT has given rise the possibility of decentralized energy trading market. This presents opportunities for prosumers and consumers to engage in peer-to-peer energy exchange. In this paper, we propose a design for blockchain-based P2P energy trading in a smart grid. Our system is centered around single-phase grid-connected smart grid that delivers 220 volt and 50 hertz output. We utilize IoT and blockchain technologies to facilitate energy trading. The inverter is designed using the sinusoidal pulse width modulation technique, and grid connectivity is established through phase control technique. The inverter section is implemented in MATLAB, while the IoT and blockchain section are developing using the Python programming language. The main contribution of this paper: blockchain-based P2P energy trading, private P2P network, implementing proof of works consensus algorithm, registration of participating IoT nodes using grid connected inverters, FET, microgrid architecture. Now, system design, grid connected inverter, grid integration, grid topology, multi inverter support with passion and blockchain. Now, the grid connected inverter section is designed. First of all, there is a performing PLL phase lock loop to get the grid angle, then dynamically sinusoidal pulse width modulation, sample table generation, which is fed to the H-bridge circuit, then LC filter. After filtering, we have to adjust a modulation index, and finally we synchronize inverter voltage and grid voltage. And on the right hand side, we get the inverter voltage, which is totally identical at that time to the grid voltage. Now, grid integration, we use phase control technique and novel technique, where active power and passive power we can transfer from our inverter. We use phase control technique so that in order to transfer active power, we have to change the angle between inverter voltage and the grid voltage. And in order to supply the reactive power, then we have to change the magnitude of inverter voltage and grid voltage. In the right hand side, grid is taking 5 ampere. When our inverter is generating 10 amperes, 5 amperes for its own load, and another 5 amperes is transferred to the grid. That's why there is a phase difference of 180 degree. This is the grid topology. As you see, there is a acronym of PCC. This is called point of common coupling, where all the grid, utility grid, and your inverters is connected. This is grid connected inverter, and this is CB. This is the circuit breaker, and there is a PCC load which is taking load. There is another features of called islanding, which is very important in smart grid area. Islanding is the condition in which a distributed generator continue to power a location even though the electric grid power is no longer presented. Islanding can be dangerous to utility workers who may not utilize that circuit is still powered. IEEE standard states that DG should be shut down in 2 seconds after main power is cut off. So basically, when the grid utility has been disconnected from PCC, every inverter, grid connected inverter, should be disconnected, and that means CB3, CB2, CB1, CB4 should be disconnected, and it's operating its own load, and that is called the islanding. because otherwise when the maintenance workers come to maintain this PCC, this is still energized because they are this is the closed circuit. So that's why this is islanding feature, and it should be maintained strictly. Otherwise, it is life hazard risks for utility workers. So there are two types of islanding detection. One is detection detected by utility company using fiber optic cable or power line communication, and IoT or supervisory control and data acquisition. And there is another technique called local detection detected by client's equipment. There are two types of local detection. One is called active, another is passive. In this paper, we actually working novel logistic regression based machine learning technique, passive islanding detection technique. I actually skipped this one because it's take long time. There is a 3 parameter we use: frequency, rate of change of frequency, and rate of change of power. In that parameter, we actually finally use the logistic function to get the whether the grid has been failed or not. This is the IoT section. I worked in my lab, power electronics lab. Here the most important part is for IoT section. I use Atmel 32 microcontroller, which is very low cost, only 80 taka in here, less than $1. So, and I use the USB to TTL converter. So this is my actually the IoT section, and this is actually in this serial communication we actually communicate the whole the battery voltage, current, power. You can get that. And as you see in the right hand side, which is totally pure sine wave, which is very and very low TSD, less than 1% TSD voltage. That is very important from electrical side point of view. Now there is a blockchain. So we made grid connected inverter, grid integration, and successfully iron detection. Now we and still we get the output from the inverter section, and now we need blockchain to securely communicate to entities, to inverters. So blockchain, there is a blocks and index, timestamp, transaction list, proof of work, previous block hash, consensus algorithm, and nodes. Now blocks are consist of couple of components. Index, though it is not mandatory, it is very helpful to track the block having a sequence number. So that's why index is important. There is a stamp in blocks that transaction data was presented when the block was created, enabling it to be encrypted. Transaction or data of blockchain consists of the following key terms: sender, receiver, energy consumption, unit price, credit, event, sale, buy. This is important. Now there is a proof of work. Now, proof of work is a consensus algorithm used in blockchain network to verify transaction and prevent double spending. In a proof of work system, miners complete to solve complex mathematical puzzle, and at first miner to find the solution, broadcast it to the network for verification. The solution is then added to the blockchain. So this is the process of the blockchain. The puzzle must be feasible but relatively complex, and so that's why prover or the inverter nodes need a significant amount of CPUs. And in this paper we use to make a block, a node must try to solve the mystery of first 4 digit of the hashing result of string concatenation of previous proof, predicted proof, and previous hash. So this string concatenation of previous proof, predicted proof, and previous hash must be 0. And one important thing is that proof of work easily verifiable. All the nodes, they don't need any very much CPU power, but in order to get the random number of proof of work, that node should need CPU power, significant CPU power. previous hash block. Every block needs the previous block hash to create a blockchain. That's actually the previous hash, and it is a cryptographic hash. And in this paper, we use Python dictionary data structure to add in the blockchain. And we use SHA-256 hashing algorithm. And there's a consensus algorithm. It is otherwise known as the resolving conflict method of blockchain. It denotes the rules and regulation of the blockchain, the price of per unit energy, transportation loss, transformer coal loss, copper loss, demand charges, etc., discussed and coded previously before the block has been created. Genesis block, first block of the blockchain is called Genesis block. It is a special block because there is no previous block, no proof of work. So this is a special block. We create. It is created when the algorithm has been decided. Now, finally, the nodes. Here, the nodes are inverters. The participant node parties are called nodes. The communication between nodes are done asymmetric encryption method. We are very much each node has its own private key and public key, which ensures the transit layer security. Especially the RSA algorithm is one of the most popular method, which is based on prime factor method. We use these RSA algorithm methods. Every node has its own private key and public key. Public key, all the other nodes are participating nodes of blockchain knows its public key, but the private key only knows that particular node. It is very famous in our daily life. Google, Zoom, every platform we use, every where use this SSL encryption. This is also used in blockchain, and that's why blockchain is very difficult to break, because every nodes have its own private key. So the block creation process. So first of all, we need to decide the consensus algorithm. Then we create block. After that, we need the POW, proof of work values. Then we have to broadcast into the whole network. Every network should verify this one, and then only then new block has been added to the chain. So this is the result. Genesis block, we take random values, previous hash values 1, proof of work is 100, timestamp is taken. And the second block, inverter 1 is sending to the grid to the energy, so it's throw its messages, and the previous hash value is here, and proof of work has very random number. And the block number 3 is when the inverter 2 has given the message that he has stopped to energy. And block number 4 has also generated by inverter 1 that total amount 10 taka and duration is 60 minutes and total power given to the grid. So, and what is the unit price, and it is given to the all the other nodes. This is the proof of work in different iteration. As you see, it is totally random. You cannot formulate in any possible way. That's why it's very popular in security. So the conclusion, the suggested P2P energy trading mechanism feature a novel and straightforward design. The proposed SIM is friendly, open source, and has potential to boost productivity and competitiveness. Sorry. This paper has already published in July this year in IEEE, and which is presented in 11th International Conference on Smart Grid, is a flagship conference in IEEE, and this is my Google Scholar page where I actually details everything. Total 6 papers has been published in this whole journey. Thank you all. Thank you.
Thank you very much for your presentation. Is there any comments on questions?
Thank you for the presentation. My first question is quick. Have you used the Ethereum to set up the blockchain?
No, sir. Actually, I use very raw code and use not. I actually use the very raw code rather than Ethereum. I have a plan to use the Ethereum in the next couple of months. I am working for that.
So how you have managed the ledger, and what are the components of the ledger you maintain, and what are the distribution of the ledger storage in the different nodes?
Currently, I use Raspberry Pi and use very text format. So and Python dictionary and JSON format. I use this format. I know it is very rudimentarily, but in professional level, I have to mention Ledger international format. But currently, I use Raspberry Pi, and every nodes capture it in a textual value.
Okay, and one thing I would like to hear from you, that there's a concept of a blockchain that in the blockchain, one node must remain alive. Because it's a distributed nature and everyone is owning the data. So there's a concept that in a distributed system or in a peer-to-peer or in a blockchain, one of the at least node must remain alive. But for example, in the case of the grid, there is a power breakdown. Yeah, whole of the country or whole of the system connected to the grids comes down, and obviously it happens. Then how you will reinitiate? Any idea? Any thought about that? How will you then reinitiate your this blockchain? Because the data might lost, and you will not be able to make it resume it, I must say. So any idea, any workout for this?
Sir, thank you, sir. It's a nice question. And currently, actually, Amazon AWS, Microsoft Azure, they are actually given very good services. Try to give services. They actually in Raspberry Pi, Arduino, IoT is not still ready to blockchain because it needs intensive power for every, as you see in my slide, every single information there. It is CPU intensive. Even the latest Raspberry Pi, it's sometimes take 1 minute or 2 minutes, very rudimentary level. So they actually in a blockchain we have to give some servers, dedicated server for that, so that we use the CPU power from that one. They actually work as a node, but they have the special power, I think, we need for that.
Yes, I am totally. And actually,
Yes.
You have said yourself what I want. For blockchain, does not working seems to be the grid computing or the electricity problems like this. It has a separate infrastructure to be deployed. But overall,
Yes.
yes, James. So thank you from my side. Thank you.
Thank you, sir.
There any questions? Okay, so it's already past the time. So thank you very much for your good presentations.